High school chemistry usually introduces equilibrium with a comforting metaphor. A physical system at rest is struck by an outside force. It wobbles and eventually settles into a new, slightly different baseline. The standard dictionary definition of Le Chatelier's principle reinforces this. It states that if a system is disturbed, it tends to adjust itself to a new equilibrium by counteracting the effect of the change. We teach this as a behavioral heuristic. We tell students that the system wants to return to normal, as if the molecules possess some collective desire to restore the peace. Giving chemicals human desires is a convenient teaching tool, but it masks the actual mechanics. Molecules do not have preferences. To understand why chemical environments stabilize, we have to discard the idea of a system seeking balance. We need to look at the strict mathematical limits of thermodynamic moderation. French chemist Henri-Louis Le Chatelier formally enunciated this principle in 1884. He built his framework directly on the earlier equations of Jacobus Henricus van 't Hoff, who mapped exactly how temperature variations shift chemical equilibrium. Together, their work expanded the scope of equilibrium from simple temperature changes to pressure variations and chemical potential, tracking how energy inevitably disperses through a reaction. We are going to dismantle the high school heuristic. We will translate simple chemical shifts into formal thermodynamic protocols and map exactly how conjugate variables dictate these reactions. The principle maps how energy distributes across a reaction's internal variables, emerging from the second law of thermodynamics. The Haber process for synthesizing ammonia provides a massive-scale laboratory for testing these physics. This equation details the reaction of nitrogen and hydrogen gas. Notice the ratio. We have 4 moles of reactant gas on the left, forming exactly 2 moles of product gas on the right. Inside a closed reactor, these gases reach a state of equilibrium. The forward and reverse reaction rates match perfectly within the defined volume of the container. If an external force decreases the volume of that container, the partial pressure of all the gases spikes. The molecules are forced into a tighter space, colliding far more frequently. The reaction shifts to the right. By converting 4 molecules of reactant into 2 molecules of product, the system physically reduces the number of gas particles, which lowers the internal pressure. The system did not decide to shift right to save itself. The severe reduction in volume mathematically altered the collision probability, forcing the gases to combine and moderate the pressure spike. What happens if we increase the total pressure of the container without shrinking the volume? We can test this by pumping in an inert gas like helium. Even though the overall pressure inside the tank skyrockets, the equilibrium of the nitrogen and hydrogen reaction does not shift at all. The total pressure is irrelevant. Le Chatelier's principle dictates that the system only responds to changes in the partial pressures of the active components. Because helium doesn't react, the specific collision rates of the nitrogen and hydrogen remain completely unaffected. Temperature operates by the same strict logic. The Haber process is exothermic, releasing 92 kilojoules per mole. In this equation, heat functions mathematically exactly like a chemical product. Raising the surrounding temperature increases the heat content of the system. This alters the equilibrium constant itself, forcing the reaction to shift to the left to consume that excess energy and produce less ammonia. Whether you apply physical pressure or blast the system with heat, the reaction only counteracts variables that directly integrate into its mathematical equilibrium constant. To prove this principle as a universal physical law, we have to strip away the nitrogen and hydrogen. We must view the system purely as a collection of abstract thermodynamic state variables. This diagram outlines the first variable, the externally controlled driver, which thermodynamics denotes as L. We apply a specific change to this driver, delta L. L represents the external shock we just analyzed, like the sudden compression of the reactor's volume, or a deliberate spike in ambient temperature. The second variable is the conjugate response, denoted as M. This is the primary reaction that the outside observer actually measures. The formal proof requires a third component, an internal auxiliary moderating variable, denoted as X. True moderation is completely dependent on this internal variable X remaining unlocked, free to move and absorb the incoming energy. Thermodynamics proves Le Chatelier's principle by placing 2 experimental protocols side by side to measure the exact impact of the driver. We start with protocol PN, the unmoderated state. In this theoretical setup, the moderating variable x is artificially locked in place. It cannot change or absorb anything. The driver strikes the system. Because the internal shock absorbers are disabled, the conjugate variable m suffers a massive runaway response. We record this full raw impact as delta m. Now we run protocol PI, the index condition that mirrors the real world. We apply the exact same driver, but the internal moderating variable x is unlocked. It is free to shift. Because x was allowed to alter its state and absorb a portion of the driver's energy, the resulting outward shift in m is significantly dampened. This creates the strict inequality that defines the principle. The absolute value of the moderated response will always be mathematically less than the absolute value of the unmoderated response. Le Chatelier's principle is a rigid inequality. It guarantees that within a closed system, internal state variables will always spread and dissipate applied energy. Because the math is so reliable, it is easy to assume this guarantee applies to all stable systems in nature. But the formal thermodynamic proof contains a highly restrictive condition. The system must be closed, isolated, and resting at a true thermodynamic equilibrium governed by cardinal entropy. Chemists Ilya Prigogine and Théophile Dedonder analyzed systems that appeared stable, but were technically just in a stationary state driven by constant macroscopic flows. A constant flow of new energy or chemical reactants alters the math entirely. If you drop an obstruction into a fast-flowing river, the continuous kinetic energy crashes against the obstacle, creating chaotic turbulence. Prigogine demonstrated that these flowing, non-equilibrium states can exhibit anti-moderation. Applying a shock does not guarantee the system will dampen it. The flow dynamics might actually amplify the perturbation. Assuming Le Chatelier's rules govern all open, dynamic environments ignores the strict prerequisites of local equilibrium. Le Chatelier's principle remains an incredibly precise predictive tool, provided you are operating entirely within its proper thermodynamic jurisdiction. Whether you are watching industrial gas volumes compress in the Haber process or mapping how abstract variables absorb a driving change, the mechanism is entirely passive. This passive dissipation of energy has nothing to do with the active, energy-consuming processes of biological homeostasis or the deliberate constraints of an economic model. Chemical systems do not possess a desire to find balance. In the closed physics of our universe, energy simply obeys the calculus of moderation, continually fracturing and dispersing through conjugate variables to protect the baseline of equilibrium.